Okay. Okay, so we're going to finish up on this topic called test for concavity and second derivative test, which in a sense kind of related to what we did on Friday. And then that will finish our new topics before our quiz. So I had you guys pick up the quiz review. I don't know. A lot of us may not be here tomorrow, even though we're running a modified bell schedule. We're going to start the quiz review tomorrow, but we still have Monday and Tuesday to review. So, but I want to give that to you early in case you're not going to be here, or if you want to get started with the quiz review. The keys are attached, and I'll also upload videos from previous years going over those worksheets if you want to watch those. Okay. Okay, so let's turn to page 17. And this is called the test for concavity. I say concavity test at the top, but the test for concavity is probably the better way of saying it. Now, we did the first derivative test last Friday, and that was working with first derivative function alone, finding the derivative, testing our intervals, right? And then looking at the sign of our derivative and letting that guide how our graph is going to look. If we see a negative from our test point, we know our graph is decreasing. If we see the graph with a positive f prime, that we know the graph is increasing. And if we see the arrows, we know how the graph is going to move. So in this case, last problem that we did was we see that our graph is going to rise, followed by falling. We know there's a relative max here. There's neither here, but we also knew that was coming from a vertical asymptote. And then the graph is going to fall, hit a relative min, and rise again. So we're still going to work with the sine line, but with the second derivative function, which is giving us a slightly different set of information, still about the same graph, but a different set of behavior. So it has to do more with the curvature than with the slope. But let me ask you this. This curve here, what slope is it showing? Positive or negative slope? Positive slope. Okay. What about this graph?
Still positive.
Still
very it's like getting less.
Right, right. So we see, obviously these are both positive slopes, but we can also tell distinct differences. This graph, the graph, yeah, potentially exponential, but also this graph is the slope is becoming more steep, right? Becoming more positive. You can, if you draw tangent lines to the graph, you can definitely see that the slopes are becoming more positive. Here, the slopes are positive, but it's, like Connor said, it's becoming more gradual, right? It's becoming less steep. So the direction of the slope change is different, right? This is becoming steeper. This is becoming less steep, but they're both showing positive slopes. So these functions are both increasing. That is true. However, the rate of their slope is different. So that goes to the two shapes that we want to talk about. The first is called a shape that is concave up. So concave up is a shape that kind of resembles a parabola that's opening up. Okay. And here's the behavior is that the slope is becoming more positive. That's how we know a graph is concave up. Or how about this? The slope is moving in a positive direction. So I'm going to give a ballpark, isn't obviously not very accurate, but just a ballpark slope calculation. So you can kind of see the behavior in that sense. Let's say this point is a really steep negative slope, right? Let's say -4. Then it goes to -3, then -2, then -1. Eventually it's going to go to what? 0, because this is 0 slope. But then after that, it's going to obviously become positive, right? 2, 3, 4. Now look at these numbers here. These are obviously not accurate, but you can kind of see the movement of these numbers, right? These numbers are all moving towards what?
Or infinity,
Yeah, but it's moving in which direction?
the right, left, right.
Yeah, it's moving to becoming more positive, right? So if these were numbers on a number line, then you're going to be moving to the right. But these represent the slope values, right? Not the y values. These are the slope values, right? So negative slope of -4, all the way to slope 0, then slope 1 to 4. So as long as your slope is moving in this direction, then this is what the graph's going to look like. It's going to have that U shape about it.
So the y and x value would be infinity.
Yes, that's right. The slope is moving towards infinity. Yeah. But you see the slope behavior is causing the graph to look a certain way, right? Okay, now the other shape is a graph that is concave down. And what do you think the slope is going to behave in this one? The slopes is now going to become what? Yeah, it's going to be, it's a move in a negative direction. That's right, becoming more negative. And you know, we always read the graph from left to right. So let's say this is a slope of a +4. Then it goes to 3, then 2, then 1, then 0, then -1, then -2, then -3, then -4, right? And you see that, you know, these slope values are moving in the negative direction. And when that happens, this is what the graph's going to look like. It's going to have that upside down parabola shape. It's going to have that upside down U shape.
Why is it positive on the left, negative on the right?
So here, what do you think the steepness of the graph is? Is this showing a positive steepness or a negative steepness?
Oh, it's going up actually.
It's going up, right? So that's positive slope, right? And so here, there's still positive slope, but it's becoming less steep. And this is obviously slope 0 because it's flat. But then as you're falling, your slope is negative.
Okay, so they're not y coordinates exactly. They're like
No, these are definitely not y coordinates. These are slope values. Yeah. Slope values. Oh, so yeah. So if you're thinking these are y coordinates, that doesn't make sense, right? This 4 should be up here, right? Not down here. Yeah. So these numbers that I'm writing down are slope values. Does that make sense? Okay. So when the slope values move in that direction, in these directions, this is what your graph's going to look like. Okay. Now let me draw another graph here. And again, I want to show the slope approximations here. This is the slope of 4 potentially, then 3, then 2, then 1/2, then 0, then -1, -2, -3. But then eventually, this is going to eventually go back to what? -2, -1, back to 0, right? 1, 2, 3, 4. So you see that this graph is moving in the negative direction, but then at some point it's gonna turn around and start going in the positive direction. So this is where what we call a point of inflection. The point of inflection is where your concavity changes. So imagine where the graph is going to change from upside down U to a right a U right side up, or you can think of it this way: if it goes from concave up to concave down, it's that point of interchange where the slope starts to move in the turn around and starts moving in the other direction. We call that a point of inflection. Okay, so point of inflection is that point where the concavity is going to change.
Is that a positive one? Like,
Sorry?
is that a positive one? Like, I mean, right by that circle. Yeah, it goes like 4, 3, 2.
Yeah, 4, 3, 2, 1. Yeah, this is a slope of 1 here. I was putting 1/2, but yeah. Okay, so here, this is going to be -4, -3, -2, -1, 0, 1, 2, 3, and then 3, 2, 1, 0, -1, -2, -3. So here you see that the slope value is going to, at some point, it's going to change. And instead of heading towards a positive number, it's going to start heading towards a negative number or becoming more negative. And we also call that a point of inflection. But visually, it's where your curvature changes. So that's what we're trying to do with this test for concavity. We're trying to determine in which intervals are the graph going to behave in these certain shapes, and where are there going to be these points of inflection. Okay, so this is what we're going to do. We're going to do this pretty much repeat the same steps that we did with the first derivative test, but we're doing everything at the second derivative level. So what we're going to do is we're going to find f double prime, set f double prime equal to 0, and these will give us critical points, and these critical points could be the potential points of inflection. We're going to put those critical points onto our f double prime sign line. We're going to test each subinterval, and then positive would mean concave up, negative would mean concave down. So second derivative function is not going to give us information about where the graph is going to rise and fall. It's going to give us information about how the graph is going to curve in those intervals. Okay, so let me walk you through example 1. Find the points of inflection of our function, and we're going to find the intervals of concave up, concave down. All right, so because we're asking about concavity and points of inflection, we have to move our way to the second derivative function. So once we find f prime, we're going to keep going, okay, until we get to f double prime. So we're going to have to go through power rule twice. So let's find f prime first. All right, what's the first derivative here?
-10x plus it's 5x.
Mm-hmm. X squared, right? All right, we can do some cleanup here. This becomes -10x to the 4th plus 5x squared. Okay, we're halfway there. We got to keep going to our destination, f double prime. Second derivative is
-40x to the third plus 10x.
Mm-hmm. Now we're going to find critical points the same way that we do f prime. We're going to set our second derivative equal to 0. Now, if there was a denominator, we would also set that equal to 0. But here, there's no denominator, so it's just the numerator equal to 0. Here, I can take out a GCF of -10x You don't have to do negative 10x. I like to do negative 10x just to allow my first term to be positive inside the parentheses. So this will give me 4x squared minus 1. Okay, I'm dividing negative 10x from both these terms. I'm left with 4x squared minus 1. Okay, any questions so far?
What's the difference between like this one and like that first?
Yeah, so the first derivative test is going to give us information about the slope movement of the graph. And the second derivative is going to give us information about the curvature of the graph.
You go about them the same way though?
Yes, about the same way, yeah.
But the process is the same?
Process is the same. Yeah, exactly the same, but the information that we're getting is different. All right, so we're going to set both parts equal to 0. This is obviously just going to be 0. And this one, can divide both sides by 4, take the square root. Don't forget, plus or minus is going to show up. So I get plus or minus 1/2. So now I'm going to place all this onto my second derivative sign line. Place my critical points onto my sign line. Now, what I've placed here, these are potential points of inflection. Okay, these critical points are potential points of inflection. I'll put that here. Critical points. Just like how from the first derivative function, the critical points are potential relative extremas, relative maximums. But here, with the second derivative function, the critical points are potential points, POIs. I'm going to abbreviate points of inflection now as POI, so I don't have to write as many letters. But the reason that I want to say potential is because just because these are on these sign lines doesn't mean that these are points of inflection. There has to be a change in what? Yeah, change in concavity in order for it to be a point of inflection. So we have to go and test the signs before we can confirm that these are points of inflection. So just like with the first derivative test, we're going to pick points in each subinterval. So here I can choose -1 as my test point. Here I'm forced into a fractional value. I'll choose -1/4. And again, these test points are not going to serve any other purpose except to help determine the signs in each subinterval. After that, we're going to cross them out. Any intervals of concavity are just using what I wrote down in blue, the critical points and infinity. We're not going to use the test points for anything else. Okay. Now, guess where these test points are going to be plugged into? Second derivative, good. So second derivative is going to give us information about concavity, so it needs to go into the second derivative function. Okay, so I'll insert -1 in for x. The -10 is obviously negative. -1 is also negative. Now here, if I plug 1 in for x, I get 4 minus 1 is positive. So negative times positive. That's only 2 negatives, which is positive. So my graph is going to show a positive concavity in that first interval. Now, as a reminder, as that the plus doesn't mean slope, I like to also give a visual connection of what the graph looks like. So I'm going to draw a U here to indicate that in that interval, my graph is going to have that shape. It's going to have that U shape in that interval.
I hadn't known it.
Because this is showing a positive value. So a positive concavity is going to mean concave up.
But it's down the second part of it. So.
But we'll go through a test and see if it ends up being negative. If it is negative, then the graph is going to have that concave down shape. Okay, so let's insert -1/4 in. -10, that's up. That's -10 times -1/4. That's 2 negatives. It's positive. Now 4 times 1/4 squared. That's 4 times 1/16. That's going to give you a value less than 1. So 1/4 minus 1 is going to be negative. So I have 3 negatives. So 3 negatives will stay negative. So my graph actually does change to concave down, which means that -1/2 is now a confirmed what? point of inflection. There's actually a change in sign. We can call this critical point now a point of inflection. Okay, let's test 1/4. Negative times positive times negative. Because 1/4 is going to do the same thing. It's going to cause this to be less than 1, which is negative. But now I only have two negatives, which is positive. So
to confirm that's point of inflection, one has to be positive, one has to be negative.
there has to be a change in sign on both. Yeah, if both sides are showing the same sign, then this critical point is not a point of inflection. Now we can't assume that it's always going to alternate signs. That's why you have to go and test. All right, if I plug 1 in, negative times positive, there's only one negative, so we have how many points of inflection do you see? 3. And if I want to find the actual locations of these points of inflection, how would I find it? Plug the -1/2, -1/2, 0, and 1/2 into the what? Original. Yeah, original is going to give you physical location. So now we're going to write out our statements of concavity, statements of concave up, concave down, and points of inflection with the justification that I'm looking for, which is because statements. Okay, so I'm going to have us write these down here. Concave down is simply, or sorry, concave up is simply where your interval is showing a positive concavity. So we're just going to use the critical points and infinity. We're not going to use the test points as part of our statement. So concave up, my bad. These should read f of x, not f of prime. So I can change that. Okay. So we're going to write it this way. F of x is concave up. Our function is concave up on the interval from -infinity to -1/2. Union, or you can do comma, doesn't matter which notation they use. And then from 0 to 1/2. All right, so the first and the third interval. And again, the -1, the -1/4, the 1/4, and 1 does not play a role in your statements. Okay, do not include those numbers in your statements. Use your original critical points and use infinities if you need to. And here's the reasoning. Because f double prime is greater than 0, I'm looking for these justifications on the assessment. Looking for these because statements.
Are you asking those on the AP exam? So
Yeah, AP exam, if they ask you for justification, if it's free response, that's what they're looking for.
it'll be like if you get the answer right, but you get the explanation wrong, they mark you wrong for the whole thing.
No, they try their best to give partial credit. Yeah. But it also depends on how they define their rubric. So yes, they're always looking for ways to give students partial credit. Okay, so our function is concave down on the second and fourth interval from -1/2 to 0, and then from 1/2 to infinity, because f double prime is less than 0. That's the reasoning, justification for why the graph is concave down. And then the point of inflection, those y values are found by plugging them back into the original function. So sometimes I will just ask you for the x value, but if I ask you for the y values as well, then you would insert these back into the original function to get their ordered pairs. And I will give you, I'll let you use a calculator on these assessments. And the reasoning is because f double prime changes signs. You don't have to say from positive to negative or from negative to positive. You can, but you don't have to. So just saying that f double prime changes signs is sufficient. And again, make sure that you are specifying the name of what you're referring to. Don't say because it is positive, or because the graph is positive, or because the derivative, or you have to name it, right? Give it a name, f double prime. Right? Don't give it a generic name. Right? So on the AP exam, it's also looking for you to reference your functions in a very specific way. Any questions here? right, let's go to the next page. So we talked about the first derivative test, which is basically the same thing here. It's just that the sign line is at the F prime level, not the F double prime level. We've also talked about this test for concavity, which is what we just did here with the sign lines that tell us points of inflection as well as intervals of concave up and concave down. Now, there's one more here. This one is called the second derivative test. And this feels strange because it feels like what we just did should be called the second derivative test, but that's not the name that we have. The second derivative test is a special test that we don't use as much, but it is important because it is part of what can be covered on the AP exam, or what can show up on the AP exam. Now this is different because the second derivative test is a name for a test that tests for relative max and relative min. It doesn't test for point of inflection. So it does the same thing as the first derivative test, which kind of feels redundant. It's like, well, we have a first derivative test that feels completely useful. Why do we need a second one? So the second derivative test is an alternate way to find relative max and relative min, but it's using the second derivative function to do it. Okay, so let me run through this, but I will point out that this one students do have a little issue with. This is more commonly missed on tests and quizzes, and I'll show you why. And I'll point those out so that you guys are aware of it and that you can make the proper adjustments. Now, we're going to approach the second derivative test the same way as the first derivative test because we're after the same thing. We're trying to find relative max, relative min. So we're going to find F prime. All right. We're still going to test our critical points that way. But we're going to gather information a little differently. Okay. Now, let's see. Before I get to the steps, let me point out a few things here. Let's say I had a graph that looked like this. Okay. And let's say this point is at 1. So what would you say F prime of 1 is equal to? What's the slope of the F graph at 1? 0. So we know it's a slope 0. Okay. Now let me ask you, second derivative, what is this a part of? Is this part of a concave up or concave down graph? Concave up. So this is what the second derivative does. Let's say the second derivative is equal to, let's say, 5. Okay. That number is going to be abstract to us. We don't really care about the numeric value. We care about the fact that it's positive. So the second derivative test tells us this. If I can guarantee that the slope is 0 and the concavity is positive, then the graph has to look like this, and this point must be a what?
Point of inflection.
Not point of inflection. This is a relative what? Minimum. So
basically guarantee that slope 0 and concavity is positive.
Right. So if my slope is 0 and it's part of a concave up graph, then the graph has to look like this. And if it looks like this, then this point that we're dealing with must be a relative minimum. All right, likewise, let's say I had this graph here. What do you expect from F prime of 0? The slope of the graph at 0 is 0. And let's say F double prime of 0 is -6. So that tells us that this graph is part of a concave what? Concave down. So since the graph is concave down, I'm going to be expecting a relative what? Relative max at x equals 0. So concave down because my f double prime is less than 0, and concave up over here because f double prime is greater than 0. Okay, does that make sense so far? Now, this is where students have struggles here. The struggle here is that we see a positive number, and you want to associate positive number with something bigger. So because of that, a lot of students want to say, oh, f double prime 1 is 5, so there must be a relative max here, but it's the opposite, right? Concave up looks like this, and you're expecting a relative minimum. Okay? Meanwhile, when you see a negative for second derivative, you think negative is smaller, so smaller must be a relative minimum, but it's the opposite. Second derivative, negative means concave down. Concave down looks like this. You're not getting a relative minimum out of this. You're getting a relative maximum out of it. So I just want to point out, this is where it's easy to get thrown off, because if you associate positive with bigger and negative with smaller, you will make that mistake. But if you associate positive as concave up and you know what concave up shape looks like, then that will help you avoid that mistake. Does that make sense? Yeah.
So what's relative maximum minimum, not like absolute maximum?
They could be, but here we're not testing for absolute max, absolute min. That's a different test. That's extreme value theorem. Here we're only testing for relative max, relative min. You know, maybe the graph looks like this, but maybe the graph curves up later on, right? So we only are caring about where are the hills and valleys of the graph. The absolute max, absolute min is a different test. That's extreme value theorem. Okay, so let me walk through the steps here so you guys can see the full process that we're going to do. Okay, we're going to approach this the same way as first derivative test. We're going to get f prime, set f prime equal to 0. We're going to get the same candidates as first derivative test. We're just not going to do the sign line. Okay, so let's look at example 2. Find relative extrema using the second derivative test. Okay, so let's find f prime. What's f prime equal to? Okay. Next up, we're going to set f prime equal to 0. Remember, we're going to follow the same path as first derivative test, but we are going to diverge after we get the critical points. Okay, so here there's no GCF, but I can factor here, multiply to be -9, add it to be -8. Okay, let's double check here. 3x squared minus 9x plus 1x. That's -8x minus 3. So I have my two critical points here. I'll set both equal to 0. Now, if I want to find relative max and relative min, normally you would do this, right? You would create an f prime sign line. You would test -1/3 and 3. Okay, but we're not going to go down this path. Okay, we're going to check these candidates in a different way. Okay, this is the first derivative test. We're going to use the same candidates, but we're going to go down a different path. Okay, what we're going to do is, well, we know that these are the candidates in play, but instead of sign line, we're going to move to the second derivative function. Okay, so we're going to find f double prime here. What's f double prime? 6x minus 8. Now, we're going to set this equal to 0. No, that's something else, right? That's test for concavity, right? We're going to test these numbers into the second derivative function. So all these things kind of are connected, but the steps are very important, right? They're distinctly different. All right, so I'm going to insert 3 first. F double prime of 3. Now, I already know that these are slope zeros, right? Because I already found these critical points. These are guaranteed slope zeros. I just didn't want to go through a sine line. I'm going through the second derivative test. So I'm going to test 3 into the function, into the second derivative function. Okay, now what number am I going to get? 10. Now, this number is not important in the sense that we're not going to, it's not an ordered pair. It's not a slope value. It's a concavity value. So don't worry about this number. Worry about the fact that it's what? That's positive. Okay. So what does that mean? That means this graph is part of a what?
Relative.
Because it's concave up. Okay, so I'm going to say concave up at x equals 3. Visually draw the graph. You don't have to, but I think it really helps is to convince yourself that you're not staring at a relative max, you're staring at a relative minimum. So we're going to say relative minimum at x equals 3. Now, some students want to say this. They want to say relative minimum is 3, 10. What's wrong with that statement?
It's not an ordered pair.
Because
It's like the slope values.
not slope value is 10.
Concavity.
Yes, concavity value, which for us is not going to mean much. Okay. Concavity of 10 versus concavity of 6. In our purposes, we're not going to see a distinction. Okay. So you don't want to write it this way. If you want to find the full order pair, you got to plug 3 back into the what? Original, right? So 3, 10. The 10, we're not going to use this number. Okay. Do not use that number except to tell whether it's positive or negative. Okay. Next up, my next candidate is at negative 1/3. So f double prime of negative 1/3. Here I get -2 minus 8, which is -10. Now these numbers are, this is coincidence that one is positive, the other is negative. Okay, it's not always going to be symmetrical like that. Now -10 is not important. It's the fact that it's what? That is negative. That's less than 0. Therefore, this is part of a concave what?
Yeah.
Concave down graph.
Absolute.
Let's not say absolute.
Of relatives.
Yeah, concave down at x equals negative 1/3. Visually, if you can draw that graph, that'll further minimize the potential of you making a mistake. So concave down at negative 1/3. Concave down looks like this. This is obviously not a relative minimum. That's a relative max. So we can say relative max at x equals negative 1/3. Okay, do we recognize how easy it is to get these mixed up? Okay, so I do want to point that out because, I mean, my BC students, they just took this test and a lot of them made this mistake as well. So, you know, it's easy to get these flipped around. So I want to point that out so that you're aware of it and you can adjust to it when the time comes for an assessment. Let me do one more example here. And I'm just going to kind of show you what an AP, now, yeah, some students that have this question, like, why do we need the second derivative test when we can just use first derivative test? And the answer is, yes, you can just use first derivative test if you want to. You don't have to go through second derivative test. It does feel more, you know, kind of a, doesn't feel as straightforward, right? You kind of this roundabout way of testing for relative max, relative min. But sometimes on AP exam, they may force you into knowledge of second derivative tests where you don't have enough information to do first derivative test. So here's an example. It's similar to what I kind of showed you above. Let's say they tell you the graph is continuous and differentiable, and they only give you this information. F of 3 is equal to 6. F prime of 3 is equal to 0. And F double prime of 3 is equal to negative 21. This is all they tell you. And they're asking you, what can you conclude about that point? Okay. So I think it helps if you sketch it out. You don't have to. Some of you may already know what the answer is. I know the order pair is at 3, 6. I know it's part of a slope 0, right? So slope 0 can be a relative max, could be a relative min, could be neither. But then F double prime of 3 is equal to negative 21. This is what we're going to use to help us make our conclusion. What does that tell us? Yeah, negative concave down. So concave down looks like this, right? With a slope 0. So there must be a what? A relative maximum. This is what an AP exam multiple choice question could look like, where even if you try to do F prime sine line, you just don't have enough information. You're kind of forced into a second derivative test knowledge.
What's that one you do have a coordinate?
This one, it does have coordinate because I actually gave you the order pair. So you would say 3, 6. Now, if this order pair wasn't given to you, then the best you can say is relative max at x equals 3. Let's see. Okay, so I did not put any homework on your homework calendar, but I want your homework to be here, page 22. And I'll send out a reminder this afternoon, as well as the link to the key. So just practice with test for concavity, 15, 17, 19, 21.
Is everything that's gonna be on this?
I'm sorry?
Is everything that's gonna be on this?
On the quiz, yeah. So we've covered everything. So we're going to start our review tomorrow. Okay, come get your phone.
We start the quiz review.
Yeah, we'll start. Yeah, you can start the quiz review if you wanted to, but
Okay.
I'll start tomorrow.
I didn't know.
It's okay.
This one, which one would be similar to?
I think they're all good, but do you plan to do all of it, or do you want to do one?
I want to do all. I just want to.
Yeah, I think this one is good. Worksheet 3.
And then is it off for remote day for seniors, like all day?
Yeah, I believe it is remote day for seniors, but I'm still gonna I'll report it.
Yeah, I'll just post.
Okay.
It's never been like, you the whole day off.
Yeah, well, I don't think you're supposed to